Now continuing with our solutions of the radial equation, for each L equals 0, 1, 2 and so on, we find if we had a nodeless solution of the form here, corresponding to the lowest energy level. We now generalize. We find all possible solutions, including with nodes. So we take this trial solution here. U of rho equals C. Now this time we have C of P is now a variable rather than a constant, and which can be expressed as a power series here, C of rho. Now for some coefficient ck, we substitute above equation into the radial equation and we get this here. In collecting terms we'll get this. Now we consider the behaviour of our C of rho at large rho. The main contribution comes from large K. So we need to consider the above recurrence relation in limit of large K. We have here. A similar ratio is found by using the Taylor expansion of the exponential function here. Right, now this implies in the limit of large rho, C of rho behaves like e to the 2 beta rho, which basically explodes. Yeah, that's not good. We are looking for a function of u of rho as rho goes to infinity, but combining factors e to the 2 beta rho and e to the minus beta rho in equation use of rho, we have found a function that just explodes. Now, but that's not to worry, we can fix this. Now, onwards and upwards. Suppose reoccurrence relation generates a coefficient of, we're setting a maximum term, C max, C of K max, which is part of the recurrence relation, that is equal to 0. If this happens, all higher coefficients are 0, and C of rho will be a polynomial of order K max. Now, e to the minus beta rho decreases rapidly to kill off any polynomial function. So that's good news. So when C of rho is a polynomial, u rho tends to be 0 as rho goes to infinity. Now looking back at our recurrence, we see C K max plus 1 will be the first coefficient to vanish, if and only if 1 over beta equals K max plus L plus 1. Here K max and L are integers greater or equal to 0, so 1 over beta must be an integer greater or equals to 1. This implies that the bound state energies are here. And this is true for all bound states of hydrogen, where n is the principal quantum number. It's basically for the radial component, the radial quantum number. Now we consider the form of the radial functions u of rho and rho L plus 1 and some polynomial in rho multiplied by e to the minus rho over n, where rho equals r over the Bohr radius, where u of r equals r. This was in the last video, I think, where we mentioned this here, where the radial equation here, r n L of r, is r over the Bohr radius to the power L multiplied by a polynomial in r over a0 multiplied by e to the minus r over n a of 0. Now to find a solution in the ground state for normalization, this is basically the, well, we've gone through what the radial equation is and we've derived this here before. Now this is just something else. We're going to find a solution of the ground state for the normalization here, because some people struggle with what this is here in front of this normalization. So you're just going to do this. To normalize something, you have to integrate. Integrate it over. Here is the radial, so we're going from 0 to infinity. And so the particle has to be, so the probability of the particle being between 0 and infinity is 100%, is 1. So this is what this is here, and this is our normalization here. So it's squared over the magnitude. So we pull out this as a constant, which is a squared, and then we have this to solve, and so on and so on. So this is our normalization constant with 2 over the Bohr radius to the power of 3/2. And this you'll see in the table of normalized hydrogen solutions. Oh, here we are. Normalized Rn for hydrogen, where our values for N here and L here. So this is the first solution here. So that was, yeah, that was 2 over, I think this one, unless I've messed something up. But anyway, you get the point. Now we're going to spectroscopic notation. In the Coulomb model of hydrogen, the energy levels are only depend on n. However, we have seen that there are n squared eigenfunctions for each n. For each eigenfunction, the electron can spin up ms plus 1/2 equals plus 1/2, or down equals minus 1/2. So degeneracy of each level is 2n squared. So in spectroscopic notation, the states and eigenfunctions with L equals 0 are denoted as S, and M why have I put the M there? L equals 1 is P. No, that's not an M. I just ignored it. L equals 1 is P. L equals 2 is D. L equals 3 is F. And for eigenfunctions where with L greater, L is greater, L equals 4 or higher, the designation goes alphabetically from G. The practical eigenfunctions are specified by attaching the value of n as a prefix and the value of m as a subscript. As an example, the ground state of hydrogen is 1SO, where n equals L, L equals 0, and m equals 0. This is ground state hydrogen right here. And when eigenfunction with n equals 5, L equals 3, m equals -3, we get a 5F state and -3 for our m. But the subscript m is often omitted. So the ground state would be just 1s. Oh, and that's that for this. Please do subscribe. We've got lots more stuff to come. And I'm going to get better at these as I go along. So please do subscribe.